of Lagos. And he will speak about nonlinear anisotropic Picone type identities for general vector fields and some applications.
Yeah, okay. Thank you for the introduction. Well, I'm not yet a professor, but I'm aspiring to one day. I will be speaking on this topic as introduced, nonlinear anisotropic Picone type identities for general vector fields. Then I will mention one or two applications. First and foremost, let me just appreciate the organizers of this summer school for giving me this opportunity to come and present what I've been studying in the last 2.5 months to 3 months. And most especially, I appreciate Professor Richard Screen, who invited me to this place to on support from HMU to come and study this. So what I'm presenting is not new. I mean, to me, virtually everybody here is not new. But to me, I am new in the business because I'm just studying it. And so I'm going to make the presentation as simple as it is, okay? So that we can all follow me, and the little I've studied, I will present that. Okay, so the outline will follow this, present some introduction, then I'll just go straight to the identities that is of interest to me for now because of the applications that we want to, that I have in mind to give. So then we'll mention some applications. The applications are not new, is what we have found in literature. So we just use the Picone identity that I was able to prove, though not new with the usual method, then relate to the applications that are in literature. Okay. So, okay, I'll present that, and this is the help. Now, for the purpose of history, Picone identity, as the name implied, was named after this Italian mathematician, Mauro Picone. He lived between 1885 to 1977. Picone identity originally to him was developed to study system of second order linear ordinary differential equation, and was able to prove Sturmier comparison theorem and oscillation theory for that system using that Picone identity. Well, so because of that, the identity is very simple, but it's so powerful because it can handle so many problem models from ordinary differential equation to partial differential equation, even system. And because of that, we have a lot of generalization and extension even to the partial differential equations. And some of the applications that it has done is Addy type inequality, Rayleigh type inequality, Liouville theorem, Sturmier type comparison principle, even monotonicity of eigenvalue, existence, non-existence, uniqueness of eigenvalues, and so on and so forth. Okay, so let me just quickly show. This is the identity that Picone proved in 1910. It was published in this journal, though in I think Italian language, which I don't understand, but we have a lot of translations here and there. Even Wikipedia can find this, so it's easy to follow. So it's not a close problem at all. So we have this identity, okay, for these functions of t. Okay, the differentiable u v and the v of t is not equal to 0. So he proved this, and u and v solve this system of equation, second order non-homogeneous differential system. Okay, so and then able to use this identity up here to prove for this system Stomach comparison principle. Sorry. So, on the condition that if F is bigger than F1 is bigger than F2 and H1 is smaller than H2, then it's able to prove that, and he also proved oscillation theorem as well. Now, in 1986, Anisotropic extended that to multidimensional context for PDE, and they did the prove the. I mean, he proved this identity, established this identity. Okay, so you can have this equals to this and show that it is non-negative. So this non-negativity here shows a relationship between U and V, which is a very powerful consequence of that identity, and is used in so many theories. So in their paper also, they prove stomach comparison principle for PDE. For second order PDE, they also prove oscillation theory as well. And we also have several extensions. So in 1998, Allegretto and Huang extended it to handle p-Laplace equations and even eigenvalue problems involving p-Laplacian. So this is what the proof of p-Laplacian. Okay, they have L, U, and V. Okay, and R, U, and V, where U and V are defined as U is non-negative, V strictly greater than 0. So if you have this L, U, and V, R, U, and V, then they are equal, and also prove the non-negativity of this quantity. So, and after that, we have a lot of extension, improvement. So the nonlinear version of one, the case of Laplacian, proof in 2013 by Yang, and some other papers followed. Then Ball 2013 also proved nonlinear version of this A2, and we have other paper follows as well. Then Socrates in 14, that is my reference 14 also, they prove they apply this one to handle principal eigenvalue of a degenerate quasi-linear elliptic system. So you can say that this identity is very powerful, and that is where the interest say, okay, if this is powerful, and then what are those equations or systems that we want to solve? Can we have a fashion of Picone identity to handle such problem? So that is what motivates me to say, okay, let's study for anisotropic so that we can solve anisotropic problems. Okay, now this operator that I have here is anisotropic Euclidean p-Laplacian. So, and what can we see here is that let me start here. Let's say pk that I put here is just 2. Say for instance, it's 2. You see this guy here, this quantity disappears, and what you have here is just the usual Laplacian. Okay, so if you have p instead of pk here, then you have pseudo p-Laplacian. So the point here is that you have the derivative in the different direction, and each direction. So this one, well, that is what anisotropic, because you have things follow different directions on not like the normal isotropy that all follow the same direction. So, and well, we have one or two speakers earlier on that have talked about anisotropic Picone. So that is you understand that one. So we find this type of problem. I mean, this operator coming from fluid dynamics, yes, from image processing, computer fusion, and so on and so forth. So now we want to go. I am studying that under general vector field for sub-Laplacian. Okay, so in our case now, we take a smooth manifold. I denote that as M. Then they put volume form on that M as dx. Then there's a vector field, a family of vector field on M. So this small m, the dimension of n is greater or equals to n. So you define that, and this operator here is called canonical sub-Laplacian. Not actually elliptic, but sub-elliptic. And this operator is widely studied. So in fact, in this book I mentioned here, so that is one of my major motivations for me to study. I study this, and we can see a lot of application of where this operator appear, and it's widely studied. In fact, if you use Omadasum square theorem, you can show that it's locally apoelliptic. Okay, and by that we mean that if the commutators of iterated commutators of this vector field generate the target space of L as the Lie algebra at each point. So you have that. So then you can even study that other weaker assumption than Omada apoelliptic condition. You can without that you can do that. Then there are several settings where you can have this type of vector field. Yes, stratified Lie group, polarizable Carnot groups, where you have feasible group, you have type groups, even cruising plane, where you can have in this kind of cruising plane, which does not even have a group structure. So you can do that. Okay. So now we are on that. This one is sub-Laplacian, and for this sub-Laplacian, we can also define P as sub-Laplacian, okay, for Pk, and Pk ranges from here to n. K is from 1 to n. So you have this. This is called anisotropic P sub-Laplacian. Just like I mentioned the other time, if you have P equals to 2, then you have P sub-Laplacian. That gives you L. Yeah, that's what I call L2, which is just the N. If you are on Rn, you have the Laplacian. If you are on the M here, then you have sub-Laplacian. So in this case, M equals to R, our volume form here is just the best measure, and this vector field is the gradient, the Euclidean gradient. Then you have that. So it's something that we are all familiar with. Okay, then the motivation literature, we have this, as I mentioned, this book is an inspiration. Then we have a series of papers by Professor Richard Scale and other people in the group, Sabitek, Suragan, and some other people. We have papers that I studied to have, to get deep insights to this field. Okay. Now, I want to present the Anisotropic Picone identities. So, let's take a bounded domain of M. M is the smooth manifold that I defined earlier on. So, we take a bounded domain. Then we define two non-constants that are differentiable almost everywhere in omega. Then let's place the following identity, the following potencies. Yeah, we have two functions, gk, fk, okay, from r plus to r plus. There's both C1. Then they satisfy this. Okay, if you pick gk, let's say you have anyway for to I put you here because I will use u and f in my statement. But let's just say you have s coming from r plus. Say gk of s is positive for s is coming here plus positive. So you have that in omega. Then on the boundary you have this gk, the gk prime, that is ordinary derivative of this equals to is 0 on the boundary. Then you have fk also in the boundary. So we don't need this whole FKV here in the presentation of the boundary. We don't need anything. So it's okay if you have the value in the interior. Okay, then the hypothesis H2, I have this quantity, this inequality, and of course, in the proof, in fact, it's very clear the way we have this inequality is as a result of some of the tools that we use in the proof. Though I have not stated the theorem anyway, but I'm just giving the hypothesis. So this inequality must hold for what I want to state. Okay, now we define two quantities, R and L, as follows. R is this, L is this. So then we have this, R equals to L and is greater or equal to 0. So moreover, that's a part of theorem 2, LU V equals to 0. Yes, almost everywhere in omega, if and only if we have this. If U is a multiple of V, yes. If you have this equality, then you have this equality, then LU equals to 0. So that is basically the theorem that we added. And the proof of this is it also follow the normal way of proving Picone identity. Yes, what do? You can just say, okay, if you go back to R equals to this, you can expand this. You can do this. This SK, this is a differential operator, yes, in direction of K. You can do this. Once you do that, expand that, K, rearrange, then you have this quantity. So the equality is straightforward. Then for the inequality part, then you can apply Young's inequality, okay, and you handle that. This is anisotropic. Yes, your inequality holds for pk. You can just have 1 over pk plus 1 over qk. Both of them are Oda's conjugates. Then you'll be able to do that. So that is by the way of proof. Then those conditions come, and to show the equality, then you have these conditions. So now I want to give remark on this, that this anisotropic anisotropic Picone identity generalizes a lot of identity that are available in literature. So we have a lot of identity. I mentioned two here for the Laplacian and for p-Laplacian. I mentioned it earlier on. Then we have nonlinear, we have different extensions. So let me just mention some of those one. If you have, yes, M to be Euclidean, okay, then and you take pk to be 2, you take gk to be u square, you take fk of y to be y. In those 5 and 6 I define, then this is the classical Picone identity. That is 1, the one for Laplacian by Anisotropic. So that's what you have. Also, if you take M to be this and you define your pk as 2, gk to be u2, then you have the nonlinear analog of, yes, because your f, if you look at, let me just go back, to mention, you can see this way. Let's look at something here and compare so that we have, look at this quantity here. So you have gk of u, which is a generalized function here. You have fk of v, it's also a generalized. So if I go back to here, look at this. So it's just up. In our case, we are having generalized function here and here. So so that's what we have here. Okay. So we have that. Also, we have this. If pk is p, yes, you have defined this to be this, you have this to be this. This has been proved also for stratified D group. Yeah. So you have this. P to be P, GK to be U, and FK to be Y. Then you have this proof. In fact, this is an earlier result by I think Neil Wang and Chang. They proved this for Isabel group. So, and you have this case for Euclidean. If you have this one, if M is equal to Rn and you have Euclidean p-Laplacian, this has proved is true. So then as well, you have things like this, so on. So we can proceed. Then I want, in the application I want to that I want to present, we will need some function from functional spaces. So we need anisotropic functional spaces. So we are having the anisotropic Sobolev space, which I guess we are familiar with as well. So and that is, we define anisotropic Sobolev space as this, okay, with respect to this norm. Now, if we have this functional, we can define anisotropic functional class D1pk 0 here to be the closure of C infinity knot with respect to the knot generated by this functional. So this is what we are going to make use in the application I want to present next. And clearly you can prove that both D1pk and this D1pk knot with respect to this norm and the other one with respect to this norm, both of them are separable and reflexive Banach spaces. So yes, the normal way of proving, and it will work fine, then we get that. So let's define the notion of weak solutions. Well, that's you consider equation of this form, then you can define weak solution by this, okay, for every file coming from C infinity. So this is the equation you have, then you can define weak solution. We are use coming as a solution in this space. Okay. Now let's do this first application. I will present just two applications. So the first one here, I want to look at the comparison, kind of comparison principle here. What we can say UV type theorem as well. So we have this system with a singular nonlinearity. So you have this, then you have this with this initial condition and the boundary condition. Okay, then we can, the proposition we have here is that this pair of solutions coming here, coming from this space, are related by this relation. So U is a multiple of this. So this is what we have, and what we apply to prove is the Picone identity I stated earlier on. Let me just summarize the proof here. Okay, since you have, this is the proof. Since you have UV as solution from this pair, okay, go by this definition of solutions. You have this 16. Okay, you have this 17, taking phi 1 and phi 2 from this space. So if you allow phi to be U, phi 2 to be GKU, GK3, because this is these are functions, you know, with the, as we define these, then phi here they are continuous. Of course, they come from here, and you can, by extension here, this as a completion of this space. So you have this, and by that, if you take U to be, you put phi 1 to be U, and you put phi 2 to be this guy here, then this is what you have. This equals to that, which will give a relation here, and you have this. And by this, you have this RU equals to 0, which implies that this one equals to 0. Yes. by this guy, non-negativity of this guy. And what does that imply? If you have this, then you have the result. When you have this, then you have U is a multiple of V, and that is exactly what we wanted to prove. Okay, so that is the first application we just stated here. So we have used that to prove a comparison principle, which you can say is Louvre type result for system here. Okay, then the second application, okay, is on the weighted anisotropic inequalities. Maybe this one can be related to what last speaker, what person presented. So, well, in a way, weighted anisotropic inequalities, we apply that as well. We apply the Picone identity to solve to prove this guy, and the condition is this: you take omega from M, open bounded from M. You take V, okay, which is a solution of this guy, subject to the initial condition here and the boundary condition here. So you have this. So, well, Fk was defined initially from R plus 1 plus as C1. Then you have a quantity Hk here, which is not negative, a weight function. For any non-negative U here, which you have GKU greater than 0. GK is also C1 as defined earlier on in the hypothesis of the identity. Then we can prove that this inequality holds. So this is any type inequality, inequality with weight, and of course this is anisotropic inequality. So, and the proof is just similar to what I presented, but the other type. So you have by Picone identity where this LUV is greater or equal to 0, you have that. Then this is by definition of RUV, you have this quantity. Okay, so by the definition of solutions, you have this. So do a kind of let's say integration by parts, you have this, and you substitute what you have here, okay, for that. So you have what's this guy, and this is what we want to. So this is because 0 is less or equals to here. I mean, if 0 is less or equals to this quantity here, then we prove this. So so that is added type inequality. Let me just quickly give a remark here. Well, if you take P to PP and D is UP, then you have a kind of this here. So this guy here is horizontal gradient. And I want to give, for example, these examples I want to give, they are not my construction anyway. They are in literature. In fact, we have series of papers by Wicharsky, Sabitek, and Suragan where they do this type of identity for Picone identity. I mean, for anisotropic, for adding inequality. Okay, so this is an example from one of the paper. Well, the example they take in that paper is more generalized than this. In fact, they did it for two weight functions. So where you have a weight here, you have a weight here. Okay, but in this case, I just try to make it simple because of the one I constructed. It's just with one weight here. And in this case, we take omega in M to be this. Then we do this kind of thing. But in this case, we need a kind of assumption on the operator L, this of elliptic. So in this one, because of this weight here, okay, which is homogeneous norm, and now we need this assumption that operator L possesses a fundamental solution. Okay, so which is very key in doing this. And when this operator possesses solution, then you can relate this homogeneous norm with the fundamental solution by this quantity here. So which you call homogeneous quasi-norm. So this is a continuous function smooth away from the origin. And for example, if you are in the homogeneous Carnot group, for example, this beta you have here will be the homogeneous dimension of the domain, which usually denoted by Q greater than 3. So that is an example. Now to prove this guy, you can choose a kind of function, okay, V. You know, if you see the original theorem, we use this kind of thing where we define F. Okay, so if you want to prove this theorem, you can choose a function V to be this. Okay, and by that we say that means rho is to the power of phi, and define phi to be this. Okay, minus of beta minus k. So what do you just do is that do a kind of differentiation and substitute this one to this original equation. And by the time you do that, then you will have hk. Then this equation will follow. This inequality will follow. Okay. Then the second example I want to give is this. In this case, I take M to be stratified Lie group. Yeah. N is the dimension of the first stratum of the group. In this case, for any U from C1, this inequality holds. It's also proof in one of their papers. Yeah. So, and in this, you have this to be the Euclidean norm of this. And the proof also follow what I said earlier on, but with different assumption. In this case, M is a stratified Lie group. Then the volume measure there is the hard measure. Then the left invariant vector V, SK, has an explicit form in this way. So this is contained in the in that book I mentioned earlier on, adding equality on homogeneous group. So you have that and all this notation. So you can prove this the way I we proved the other, the one I said, by choosing V to be this products, and you choose phi k to be this. So if you do that, substitute in that equation, then this will come with this weight and this constant. So that is yeah, I think I will start. Okay, so well, this is my monument and this is my constant. So thank you for that. Okay.
Thank you very much, Abimbola. Maybe some questions, comments?
So, your Picone's identity, is it first? It's first order, right? For the system, it is first order Picone's identity.
It is what?
First order.
First order?
Yeah, like, if it's
no, not only first order. We have
which system?
It's not only first order. You can do for higher order, especially fourth order.
Yeah, for if we do this for second order case at least.
For second order, where you
then we can expect relic type of inequality instead of body there also.
Yes, if you do it for second order here, that's for the fourth order operator. You can get a relic ad inequality, of course. Yes, which which is contained in the work. I just presented this for the purpose of presentation.
Any question, comment?
Yeah, this is a good remark because not so many identities are known for high order, so this is of course
Okay.
So let us thank Abimbola again. It seems like we have a different case today, banana cake, like I was requiring, and please go to the PhD room and we will
open and see. Check. No, how can I check? I see and I will check a picture if there was. So let me check the room.
I hope no, but wait until the professor can see it. I think that's what I can see.